Alright, here we're going to do a proof question with vectors to do with collinear points. This is a take on example 7, page 239 in book 2. It's slightly different in that I didn't actually give as many clues in this one, whereas in the book they actually scaffold it step by step, and they don't actually talk about collinear to begin with. This one's a little bit more challenging on its own, but I want to talk you through the steps, because you should be able to come up with this kind of stuff yourself just through logical thinking. So OABC is a quadrilateral in which OABC, we're going to name OA the vector A, OB is given in terms of A and B, where we haven't been given B, OC is 4B, and then we're given the extra piece of information, D is the point, so that blah blah blah. Essentially, the first thing we want to do is place all of this so that we can use it. So I'm going to call OA to begin with A. And we can see throughout all of this, we're not actually going to get any more A's because there are no lines that are parallel to that. However, we're given the information that OC is 4B, which is independent of A, 4B, and then we're told that OB is A plus 2B, which makes sense, A plus 2B. So we can actually deduce from this expression here that this up here is actually going to be 2B. I probably don't even need to write this down, but it might be useful information for later. D is the point such that BD is equal to OC. So these are two vectors that are equal. BD equals to OC, and because OC is equal to 4B, I can actually replace this with 4B as well. And then finally we're told that X is the midpoint of BC. Now this doesn't actually mean anything yet in terms of vectors, but it might be useful to know that that is the middle of BC. So already it's a little bit more colorful, but it might be a little bit more accessible because I can now navigate through all the different points using the vectors that we've defined at the beginning. So I'm going to show that O, X, and D are collinear. It's always kind of worth checking that you know what this means. This means that O, X, and D lie on the same line, and we can kind of see this even in the sketch I've done. It kind of looks like it, but in order to prove it, that's a whole other thing. Because in order to prove it, I need to show, and there are different ways of doing this, that two vectors involving different combinations of O, X, and D are parallel, and that in addition they have a point in common. So either I'm going to show that OX is equal to a multiple of OD, I could show that OX is equal to a different multiple of XD, or I could even show that XD is equal to another multiple of OD. So any of these would show me that these two vectors are parallel, but because they have a point in common, that means that they have to be on the same line as well. So it's just some combination of this. I think for this one, because everything's given in terms of O to begin with, I am actually going to use this one. I'm going to try to prove mathematically that this vector is a multiple of this vector. But in order to do that, I need to find expressions of OD and OX in terms of A and B. You'll always have to express things in terms of vectors like this. The first thing I need to do is I need to be able to express OD in terms of A and B. So I'm going from O to D. Now we remember that vectors, you can go anywhere you want as long as you use the right vectors that we've defined at the beginning. It doesn't matter how many detours we take, and here we can see it's all colored. So I go from O to A to B, B to D. That is exactly the same as going directly from O to D, and this is already paved out for us. So that is A plus 2B plus 4B. So if I wanted to write it out with all the working, I'd write this OA plus AB plus BD, and then I would just replace that with A plus 2B plus 4B. I could even have written this one directly as OB and used that definition there. So in the end, OD is equal to A plus 6B. Now with any luck, when I find OX, it'll be some multiple of this. So OX is going to be a little bit more complicated because I'm dealing with the weird region here, which is kind of unknown and undefined. So if I were to write OX like this, I could do it two different ways. Either I could go across to C and up to X, or I could go up to A, across to B, and then down to X. And it doesn't actually matter which one I use. I think this one, if I write this as OC plus CX, that would involve fewer steps, except I don't know anything about CX. But what I do know is that because it's halfway on CB, it is the same as 1/2 of CB. Now I'm going to leave that there for a second because it turns out that I can actually define CB. Because from C to B, again, it's all colored. I've used it all. So from C to B, that's going to be CO plus OA plus AB, which is, because I'm going backwards, minus 4b plus a plus 2b, which is a minus 2b. So if I go back to this one now, I've defined CB in terms of a and b, so I can write OX is equal to OC, we can see is just 4b. So it's a little bit redundant because it's like I'm going across 4b and then back half of 4b, across half of a, and then across half of b, plus 1/2 of, and then this is where I can just substitute CB in, and we find a minus 2b, which is the same as 4b plus 1/2 a, just by multiplying through, minus, and then 1/2 of 2b is going to be just 1b, which gives me 1/2 of a plus 3b by gathering my terms. So I've done all the hard work, but the conclusion here is I want to show that OX and D are collinear, and here we notice, if we look at these two, that this is literally just half of that, which is kind of what it looked like anyway, but I've proved it mathematically. I know that OX is equal to 1/2 of OD, and here it turns out I am doing it the other way around. It doesn't really matter. I could also say OD is equal to 2OX, and therefore OX is parallel to OD, but because they have O in common, OX and D are collinear. And that is your proof, but you have to write that final statement, otherwise you don't get access to all of the marks. Now, it's a bit of a complicated step-by-step thing. It depends on where this question actually drops in the exam. If it's at the very end, they might be expecting you to make all of these steps yourself. If it's nearer to the middle, they might break it down bit by bit. It depends on what difficulty they're willing to throw into this question, but it is all just finding your path using the vectors they set out at the beginning, and then showing that one vector is a multiple of another vector, using the A's and the B's. So there you go, I hope that was helpful.